correct? And then it will lead to Laplacian. So del square v. We know that this is nothing but del x I ei. So how do I write? How do I do that? Let me do this way. So del x I ei dot del xj ej, and then I have another vector which is vk ek. So I'm writing this in a total initial notation, and then these are all n-dimensional spaces. Now I know that the dot product is between ei and ej, which implies me what? This will be delta I j. Correct? Now if that is the case, then I will have del xi, then I will have del xj, then I will have vk, then I will have vk, right? Now once that is the situation, now I know I equal to j will only survive for a Kronecker delta symbol. So xi and xi will be okay. So this will become what? Del square del xi square. So these three will lead to this, and then I will have what? This will be with vk, and then I will end up with a unit vector which is ek. So here you can see that I have started with a velocity vector. If I take a gradient, I get a second order tensor, and then if I take a divergence of that, I end up getting another vector. Okay, so this will be nothing but a vector. So for one, this will be, say suppose v1. V1 means what? Say suppose I write only the x component. How will it look like? So del square v means, say suppose u, velocity u. So del x square. Okay, then what will happen? Del square u, because this is a repeated index, del y square, and del square u by del z square. Okay, and then I have what? Then I have what? Ek means e1. That means this is the ith component. So this will be my ith component. What will be my jth component? Del v del x square, del v del y square, del v del z square j. And then what will be my w component? Yes, then what will be my w component? Del w del x square, del w del z square, del w del z, del w del y square, del w del z square k. So in that process, you may see there is I, j, k components. There are three different components associated with this vectorial component. So I started with a vector. When I took a gradient, it became a tensor, and then I took a divergence, and it became again a vector. So you can see divergence always reduces the order of the tensor, whereas dyadic product always increases the order of the tensor. And if you understood that, I mean conceptually understood that, now things will become very, very easy for you. So how do I define a dyad here? So dyad, that means a second order tensor. I define like this. This is my first introduction to a second order tensor, say suppose t or tau. Okay, I define as Tij. Okay, what does it mean? This means that Tij, and then I have Ei. This is hidden. This is not there. Ei dyadic Ej. This is the unit vector. How do I look at it in the coordinate system? Say suppose this is my coordinate system that I had drawn. So when I am talking about a scalar, okay, the scalar I am talking about, this is the 0th. This is the place when it is the 0th order tensor or a scalar. It doesn't require a directionality. But moment I talk about a vector, I just need to resolve it to in three different coordinate system, that is x, y, and z. All right. Now, when I talk about a tensor, you just again see that I am now resolving now x component into three different components, z component into three different components. Okay. And again, y component into three different components. So this is where you can see that. So what I call this part, this one I called as XX. What I call this one I call as XZ component. Okay, what I call this one I call as XY component. What I call this one I call as ZZ. This one is Z towards X, that is ZX. Okay, and this one is what? This one in the direction of ZY, so this is ZY. This is YY. Okay, this one is YZ, and this one is YX. So how do I distribute? Say suppose if I write T in a matrix form, okay, so what will happen? I will have total 9 T's, right? Based on this EI dyadic EJ. So let me just first write all the 9 T's here. 9 components of the T's. How exactly this component distribution has taken place? 9 components of T's. So this will be my X. This will be my X, Y. I'm writing row by column. This will be my X, Z. Okay. This is my Y, X. This is my Y, Y. This is my Y, Z. Okay. Then this is my Z, X. This is my Z, Y. And this is my Z, Z. Right? So when I am talking about a vector, it is about X, Y, Z. When I'm talking about a vector, this is U, V, and W. This is what I'm writing, right? So what does it mean? Say suppose if I write in terms of V, say Vx, okay, comma Vy, comma Vz. So what am I doing? I am resolving the speed variable, that scalar, into 3 different components. So this is where the vector component is coming. Now when I am resolving the same variable, say suppose the gradient of V into 9 components, then I am getting into the domain of the second order tensor, where there will be 9 components. So what are those 9 components? The 9 components are associated with this. Each and every direction has been resolved into 3 different directions, which is leading to 9 for a 3-dimension. Okay, for a 4-dimensional space, what will happen? For a 4-dimensional space, each will have 4. So 4 into 4, it will be 16. Okay, so that way, 4 to the power 4, perhaps 4 to the power 4, it will be 64, right? So how many components will be there? That you keep as an assignment. For 2, it will be 4. If you have 2 dimensions, you will have 2, 2. If you have 4 dimensions, then for each dimension you will have 4, 4, 4, 4. So it will be 16. So for 3 it is 3, 3, 3. It is 9. For 4 it will be 4, 4, 4, 4. Right. So in that process, you just start getting different types of dimensional spaces, and which will be very, very helpful. When you have different types of other vector spaces, this knowledge will be extremely essential. So now we have introduced the concept of dyad. So I have given the different components here. Just go through this, starting from the velocity gradient. Okay. And then, you can do different types of operation, that if you add 2 tensors, it will add to second order tensor, it will remain a second order tensor. If you take a dot product between the 2 tensors, okay, what will happen? It will become a vector. Can we do that? Let us see how do I do that. So I have a vector. I have a tensor, say suppose sigma ij, and I know that there is EI dyadic EJ. That is there. It will remain as a tensor. Okay. Now I have another tensor, say suppose tau. Sorry, I'm doing a dot product, right? So I take a dot product. I do a dot product with respect to what? Tau mn. Okay. Then I have EM. Then I have dyadic EN. Okay, I'm taking a dot product here. So what I do, I leave this sigma ij, okay, and tau mn at one place. And then what I do, I don't change the order. see this J and M, they are undergoing dot product. So I just keep as delta JM, that is coming by collapsing these two. And then what it remains as EI dyadic EN. Okay, now once you do that, J is equal to N, so this will become what? Sigma Ij. Sorry, this will be Jm, right? This will be Jm. Sigma Ij tau Jn Ei dyadic En. So you can think about this is a matrix 3 by 3 matrix. This is a 3 by 3 matrix, but when you do a matrix multiplication, the column should be equal to the row. So that is also satisfied here. And then you can really see now what is this? This is a dyad. This is a dyad. This is second order tensor. This is second order tensor. If you take a dot product between them, you end up getting a second order tensor. Okay. But then if you take two dot products between them, then what will happen? You will have this will be replaced by again another dot product, correct? And then what will happen? You will have another. You can see that this will become what? This will become delta In. Okay, sigma Ij tau Jn, which implies what? Which will imply I is equal to N. So sigma Ij into tau Ji. So again, matrix multiplication rule is satisfied. But then now this one is what? This one is a scalar. Okay, so you can see by doing dot product between, so you can really do reduction. You can really do reduction from a dyad to a kind of scalar, second order tensor to a zeroth order tensor. Okay, so this is what is given here, that you can, this is sigma dot tau, sigma double dot tau. Okay, tau dot v in a tensor, you are taking a product with a vector, you end up getting a vector. Tau cross v, different types of examples are given for you. Just practice. These are all practice problems for you. Essentially, you may require, these are the variables that you may require in fluid mechanics, heat transfer, mass transfer, transport phenomena. Sorry, if you understand all this, you are more or less through, and that is the reason we have done this background work. So what is divergence of V? We have done a number of times. Curl of V, you know that you can write it as E1 into E3, del del x1, del del x2, del del V1, V2, V3, and it will lead to this. Gradient of V, we have done a couple of times today. Gradient of V transpose, you just reverse the matrix. This is a dyad. V is a vector. Gradient operator is a vector. When you take a dyadic product, it leads to a second order tensor. And that's a matrix, 3 by 3 matrix. If you take a transpose, that becomes gradient of V transpose. Divergence of tau. So divergence is what? Divergence is a vector operator, right? So how do I do that? This is another one that is remaining. Perhaps we can do very simply. I'm just giving you the example just to tell you that this is not that difficult. So the gradient operator, and I'm taking divergence of a second order tensor. This is tau. So generally, like if you write a second order tensor, you give two lines like that, and then for a vector you give it like this. So this is what this we can write as del del xi ei, and then I can do a dot product with what? Tau ij. I cannot use I here. I use jk. I use jk here, and then I have ej dyadic ek. Okay. Now you know that J and I will happen with what? It can be a Kronecker delta symbol. Okay, this will be a Kronecker delta symbol. From there you can really imply what? Then del del xi, and then you will have tau jk, and then you will have ek. Okay, so this means what? I equal to j means del tau ik by del xi, and then you have ek. So you just expand This one with respect to the repeated indices, you end up getting. So this is a vector. This is a tensor. If you take a dot product, you end up getting what? This is a vector. So this is a tensor. This part is tensor. Okay, this part is a vector. But then, you know, if you take a dot product between them, you end up getting a vector. So make yourself comfortable. This divergence of T and all will appear. Immediately it will appear. As you will see, we will go to Reynolds transport theorem quickly, and then it will immediately appear, and then you will see that these are all necessary, you know, arguments that you need to do. And then, you know, you can see gradient of S is a scalar, gradient of S is a vector, gradient is a vector operator, so vector divergence vector is a scalar, which is the Laplacian. I've given some more examples, just go through them. Okay. Okay. Now coming to the next 4-5 slides. You know, these are all whatever I am showing for last 4 lectures is what is required for fluid mechanics, heat transfer, you know, transport phenomena, mass transfer. These 4 subjects, what exactly you require. I'm just giving the glimpses. So some maths are given, some, you know, equations are given. Okay, so these lectures, you know, you should keep from that perspective that this is the target that has to be achieved. And as we progress in the course, I will try to resolve the issues one by one. Okay, so essentially you may see that there are 4 parts. There are 4 parts of development in terms of modeling of an engineering problem. So day-to-day life, you can see that it is explainable using a classical mechanics, and then it turned out that, you know, it is not very well established in case of when you go to the matters which are having higher speeds. So special theory of relativity came, and then this was corrected to quantum mechanics later, which is now in the form of quantum field theory. Okay, which explains most of the phenomena that is there in nature, or all the processes, you know, they follow this particular theory. However, for engineering processes, we generally follow the classical mechanics. So whatever heat transfer you are talking about here, these are all, you know, coming from the platform of classical mechanics. And, you know, we have, you know, this is in most of the situations, the results that we are using that also have been verified by quantum field theory. So these two are not inconsistent to each other. However, you get more information when you use this theory with the interpretations that you get using classical mechanics. Okay, so in order to understand Newtonian mechanics, you have to understand one particular variable very clearly. That is, you know, that is, say, suppose you have a scalar set, suppose you have a scalar temperature, okay, which is a function of time and space. So this you have to understand very, very clearly. T is a function of time, x component of a coordinate system, y component of a coordinate system, and z component of a coordinate system. Okay, so how do you write that? You write that, so suppose there is a change that is happening, that is dt. Okay, now how do you write that? You write that this is equal to del t del t by del t, okay, at what? At constant x, y, and z. Okay, and then you write this to be dt plus del t by del x. I don't write what is constant, dx. You can understand here t, y, z are constant. Then I write del t by del y dy, and then I have the last one, del t by del z dz. This is the total change of temperature. So here you may anticipate that time, you know, y, z, these are constant. Here you may anticipate that x. Okay, then what is other thing constant? Then you have x, time, and z, these are constant. And here you may anticipate that what are the constant factors? Constant factors are time and then x and y. This particular change is the change of temperature in time and space. Okay, and you can see that, you know, if I divide this particular variable, say here I am doing dt. Now if I divide, dt is this is small t. Okay, don't confuse this. Capital T is temperature, small t is time. And if I divide this with this dt, what happens? Okay, this one goes out. I have dx by dt. Okay, I have dy by dt, and then I have the dz by dt. Okay, now dx by dt is what? This is u velocity. Dy by dt is what? This is v velocity, and dz by dt is what? W velocity. So you may see, although this is written as concentration here, so dc by dt is nothing but the change. What is this? This is the local change. For a fixed point x, y, z, what is the change with respect to time? That variable c can be temperature. So this is multiplied with what? The change that is happening, this dc by dx. In x direction, how much is change? Y direction, how much is change? And z direction, how much is change? Now these three variables are multiplied by what? Vx, Vy, and Vz. This is appearing by definition. So this is the local change, and this particular change is called this is the local change, and this particular change is called the convected change. Okay, so you can really see any variable c. If I really make it as a function of time and space, t, x, y, z, one part will be associated with the local change, and one part will be associated with if there is the fluid that is moving. If the velocity is 0, then this derivative is equal to this derivative. But if Vx, Vy, Vz exists, then there will be some change of that scalar, that is c. Here it is concentration, it can be temperature, it can be u, v, w, any of the velocities. Okay, which leads to what? Which leads to, now you can see that this dc by dt is called the substantial derivative. Okay, or the material derivative. Okay, now what is dc by dt? Dc by dt is nothing but del c by del t, the change, local change, with what? You can write this as v dot. This is nothing but del c by del x I, del c by del I, del y j, del c by del z k. This you can write nothing as a gradient of c. C is a scalar, gradient of c, that's a vector. And then v, vx, vy, vz, vxi, vyj, vzk. Now I think you are comfortable with this, that you can write v dot del c. So the total change in time and space is the local change and the convected change. In order to make you understand, last two classes, this particular thing, you know, last two classes were spent just to make you understand this part. So if I start with a variable c, if I really want to see what is the change with respect to time, the change with respect to time is like this. This is the change, the normal differential, which is a culmination of what? Which is a culmination of all partial differential. You know, I just partial differential what? I'm just, you know, accumulating bits and pieces. What is varying? If I fix space, what is varying with respect to time? If I fix time in x direction, how much is changing in y direction? So it is like I am just doing housekeeping of every directional change. And then if I just cumulatively put in together, then any change of scalar with respect to time is nothing but the local change and the convected change, which is by definition coming from the mathematical definition. Okay, so d dt is called total time derivative. Capital D by dt is called the substantial time derivative, and this is the onset of the Eulerian framework or the Newtonian framework on which, you know, all the analysis are done. Okay, so you can very quickly understand the differentiation between the ordinary differential, which is a generic form like this, and say suppose if you are really writing, so your essential framework is here. The entire framework that we are going to use is the partial differential framework, and this is the most generic form of a partial differential equation you can write. This is a second order partial differential equation you can write, and you define the PDAs into three different types. Now in this definition, if based on these coefficients, if b square minus 4ac is greater than 0, that is called a hyperbolic equation. B square minus 4ac equal to 0, that is called a parabolic equation, and b square minus 4ac less than 0 is called an elliptic equation. Okay, and if A, B, C are functions of what is an independent variable? This X, Y, these are all independent variables. So this A, B, C, if they are either constant or functions of X, Y, then this PD is called a linear PD. If this A, B, C, D, E, F, G, these are functions of phi, then this is called a nonlinear PD. The coefficients functions of phi is called the nonlinear PD. Now, if I enforce b square minus 4ac less than 0, I will end up getting an equation like this, which is the Laplace equation. Del square t by del x square plus del square t by del y square equal to 0. Famous heat conduction equation. Okay. Now, if I replace b square minus 4ac, b square minus 4ac equal to 0, if I enforce, I end up getting a parabolic equation, which is del phi by del t equal to alpha del square phi by del x square. Okay, this is the transient heat conduction. As phi replaced by t, you will get that this is the lump flow. You know, unsteady heat conduction, this is the equation. Okay. And the third one, del square t by del t square, okay, equal to c square del square t by del x square. This is called the hyperbolic equation. Here I am enforcing what? I am enforcing b square minus 4ac is greater than 0. So this is called the hyperbolic equation, which is called the wave equation. All the convected form, this particular form, here what you saw, this particular form, this is nothing but the form that I am showing is a hyperbolic situation. Okay, so PDs are of three types. So this is a linear PD, elliptic PD. This is a linear parabolic PD, and this is a linear hyperbolic PD. If this c square and if this alpha is a function of phi, then this will become a nonlinear parabolic and nonlinear hyperbolic equation. So essentially, I stop with this slide that you have to go for the conservation. Now we are ready. The background maths we have done. We have bits and pieces, the equations for conduction, convection, and radiation. Okay. So next class we are going to start with the conservation of mass, momentum, and energy. We will ignore mostly momentum because you are doing in fluid mechanics. We will quickly see mass and then go to the energy equation. Okay. We are going to use the concept of continuum, and this energy equation will take up towards conduction and convection. Okay. Yeah. Any question you have right now? You have any question? I stop here today because it's almost time. If you have any question, you can ask. You can raise your hand too. No question? Yes. Anish, please go ahead.
Sir, when you told about the change in temperature with respect to time, one part was the local change in temperature and another part was the convected change.
Yes. This slide, correct? Hello? You're talking about this slide? Anish, are you there? You are muted. I'm unable to follow you.
Hello, sir.
Yeah.
Am I audible?
Yeah, you are audible now. So you are talking about this slide, correct? Hello?
And in this slide, the velocities that we were mentioning, were those velocities the particles that actually have the temperature?
Yes. So suppose you have room is filled with air, correct? And so suppose this air can be there can be two different types. One is air is stationary and the second is air is flowing. Now when the air is stationary, this Vx, dy, Vz is 0. So you will only have temperature change, which is local temperature change. Whereas if the wind starts blowing, what will happen? This temperature, say suppose at one place you have high temperature, but if the wind is flowing, what will happen? This temperature will propagate not only because of conduction, but also because of convection. Because of the flow, it may flow somewhere else. Okay. Now this part is taking care of that, which is called the convected variable, which is called the convected heat flow. Okay. So
Okay.
if there is no fluid velocity, this will be 0. But if there is a velocity, if there is a movement, what will happen? This variable C, it can be concentration also. So suppose you have put some sort of incense. If the entire air is stationary, the incense will just diffuse. That is one way of doing it. We'll come to that. But the other way around is like, say suppose if there is any flow, what will happen? The incense will start flowing from one place to the other place, correct? Now this part takes care of that. And then what does it happen? I start with a basic definition that if T is temperature is a function of time and space. So this is the local variation of temperature with respect to space, whereas these three are what? These three are the convected. So they are essentially convected. So this part is the convected. If I replace this C with T, this C with T, this C with T. So if C is a scalar, this is the convected variable, and this is the local variation. Is it clear for you?
Yes, sir.
Yeah. Any other question? Since there is no more question, so thank you. So we meet at 11 a.m. sharp on Friday for the tutorial. Thank you. Thank you so much.